Okay, so the question we asked ourselves was whether a barotropic surface tide interacting with geostrophic eddies could possibly excite an internal tide or a baroclinic tide. Okay. Okay, so first I'll give you the motivation for this problem, the oceanographic motivation. Then I'll present the weakly nonlinear theory as a resonant triad interaction. I'll explain to you how we separate eddies and the tides, go through the details of multiple scale analysis, and due to some technical problems, I probably won't be presenting in the talk the numerical simulations, but I'll be very happy to show you movies afterwards. I had multiple problems inserting graphics into my LaTeX document last night. So, all right, so the motivation, first of all, let me just say that there have been lots and lots of studies that have shown that a barotropic tide can interact or can scatter off of topography and generate internal waves, and that's a very efficient mechanism. Okay, so that's an example of a bottom inhomogeneity. It's a scattering problem off of bottom inhomogeneity. So the problem that we're looking at is similar, and it was motivated by a number of papers by Rogachev et al. Dating back to 1992 and all the way to 2002, that speculated that in their observations, the diurnal tide internal waves, or the diurnal tide frequency internal waves that they saw could possibly be generated by the interaction of the tide and nearby eddy fields. So the caveats in those observations was that they had very limited data, so they could not rule out wind forcing or various instability mechanisms. And they also didn't provide any type of theoretical argument as to why this could happen. I'm going to need some water. Thanks. So that was the motivation. So what we asked ourselves was, very simply, can this mechanism be an efficient exciter of an internal tide? Under what conditions? So that was the motivation for our study. Thank you. It's a different climate up here. So the problem as we see it is sketched here very simply. Okay, so that's a horizontal cross-section, and that's a vertical cross-section of, say, a typical eddy field. Okay, so we have an eddy field with a particular scale. Typically, the eddy field has a low frequency compared to the frequency of the barotropic tide, and it's got some characteristic horizontal and vertical scales, which I've indicated here. So typical horizontal scales are on the order of 150 kilometers, and typical vertical scales are on the order of 1,000 meters. For the barotropic tide, on the other hand, the frequency is fixed. It's barotropic, so it doesn't have any vertical variation. And for now, I'll just leave the horizontal scale of the barotropic tide to be unfixed, okay? So here we have this eddy field, and then we have this tide.
What's plotted?
This is the velocity field. I think it's the V component of the velocity field. So, like so. Okay. What else should I say? All right. So, the problem as we envisioned it is that we have an eddy field with some specific length scales, we have a barotropic tide with a specific frequency scale. If the length scales of the barotropic, if the length scales of the eddy field are such that the resonance condition can be satisfied, like so, then we'll have resonance. I didn't say that. Okay. And the waves that will be excited in this case will pick up the components of the eddy field in the horizontal and in the vertical. Okay. So this is very similar to a resonant wave triad interaction, first studied by McComas and Bretherton and by numerous other people. Okay. So this is the mechanism envisioned for internal tide generation in our problem. Louder? Okay. So the model, as we set it up, is just a 3D Lucent model, and we're going to introduce the tide as a forcing term in the zonal direction, like so. And so the tidal forcing will just take to be some amplitude, and this particular form is designed to give us just oscillatory, time-dependent behavior with some characteristic horizontal wavelength. Okay? The eddy field, on the other hand, will be introduced just as an initial condition. So here I'm just giving you the simplest initial condition possible. It's just a modal initial condition. Okay? Like so. So the eddy field has then these characteristic scales K2, L2, M2, like this. And the eddy field initially we impose to be in geostrophic and hydrostatic equilibrium.
That's not like your picture, Pascal, where
No,
there's
it's
only
not.
one road.
Right,
Your
because
eddy's filling the whole thing.
yes, for the weakly nonlinear analysis, I'm just going to demonstrate it filling the whole thing. For numerical simulations, to see the propagation of waves away from our eddy field,
Okay.
we impose some kind of ramping function in in X and Z. All right. So we've decided to formulate this as a multiple scale problem because the eddy field evolves on a very slow time scale. The tide, on the other hand, evolves on a time scale characteristic of waves. So here I've introduced a fast time scale, which is proportional to the inertial time scale. I could have picked the tidal time scale, but the equations simplify. The natural time scale of the equations is this one, and so the equations just work out to be nicer in this time with this formulation. And we can define a Rossby number to be the ratio of those two time scales, and then in the usual fashion we'll just expand all variables as a series in epsilon, okay, like so. And so the tidal signals, both barotropic and baroclinic, will depend on the fast time scale as well as the slow time scale, whereas the eddy field will only evolve on the slow time scale, okay? And in this formulation, the barotropic tide will come in at lowest order, as will the eddy field. The internal tide will come in at order epsilon, and if there is a resonance, then in time that baroclinic tide, that internal tide, can become order 1. Okay. So how do we delineate these various components? Well, the simplest thing to do for the eddy velocity, for all eddy variables, is just to average over the fast time. Okay, so we do this like so, just by definition. So, and for the barotropic tide, what we do is that we take the vertical average of the flow field. The baroclinic tide then, well, let me just point out something. This is actually related to the Crya herring decomposition. You can think of this as being the rotational part. So the eddy, the time averaged part is the rotational part. The sum of the barotropic and baroclinic tides constitutes the divergent part of that decomposition, with the baroclinic tide just projecting onto the high wave numbers and the barotropic tide just projecting onto the lowest wave number. The baroclinic tide can also be described by a forced wave equation, and at lowest, and it accounts for all of the vertical velocity at high frequencies. Okay. So here is, we can derive just through algebraic manipulations from the equations of motion, a forced nonlinear wave equation, like so. In yellow, I've indicated the lowest order operator, and then the forcing terms definitely come in at higher order, and I've listed them here. So they represent all kinds of things from, but the most important one in this formulation is this one right here, which, if this were a dimensional quantity, if I were in dimensional space, there would be a Coriolis frequency parameter here. Okay. And so what we're going to do is to look for internal wave excitation by looking for the projections of these right-hand source terms onto the high frequencies, okay? And as in this paper, Ford et al. 2000 pointed out, in order to have high-frequency waves excited from this equation, we must have projections onto these high frequencies, okay? So not all solutions of that equation are inertial gravity waves, obviously. Okay, so we can write down the lowest order equations for the Eddy field. These are just the geostrophic and hydrostatic balance equations. For the barotropic tide, we have this forced set of equations, and for the baroclinic tide, we just have a homogeneous wave equation. So, and the lowest order solutions, as expected for the Eddy field, they don't vary much from the initial condition. Coefficients depend on the slow time. The barotropic tide signal consists of tidal ellipse plus some natural modes of the system, these inertial oscillations. And because the baroclinic tide obeys a homogeneous linear wave equation, and with zero initial conditions, there can be no waves at this order. Okay, so when we go on to the order epsilon equations, so the operator on the left is the same as for the order of one solutions, but now we have forcing due to these terms over here, which represent the variation of the lowest order solutions with the slow time and the advection terms, okay? And the barotropic tide looks similar. These double bars indicate vertical averaging. These single bars indicate temporal averaging, like so. And so, since we're mainly concerned with the generation of internal waves, let's just go directly to this order epsilon equation, which now picks up three contributions from the right-hand side. And the full right-hand side terms contain eddy-eddy, tide-tide, and eddy-tide interaction terms. But because we must have a projection onto the high frequencies and also onto the high wave numbers, the only terms that can contribute to force waves are the eddy-tide terms, okay? And so the resonant terms, or the terms that give resonant behavior, are of this form. They're basically e to the I k2x plus or minus L1 plus L2y plus or minus blah blah, like this, with slowly varying coefficients, which we must solve for. Okay, and we can plot the resonance curves, that is, the values of L1 for which resonance is satisfied. Here I've just indicated the wave number of the Eddy field as a function of theta. And here I've plotted just the locus of all the points, of all the values of the horizontal variation of the tide as a function of this angle theta. And so you see that it's symmetric about the angle pi. And it has, so L1 has maximum values when the angle theta is equal to 0, which corresponds to essentially a vertical wave number for the Eddy field, like this. And going back to the coefficients of the resonant forcing terms, we see that they assume a pretty complicated form like this. But right away what we can see is that if L1 is equal to 0, that is, if the baroclinic tide or the barotropic tide does not vary at all in the horizontal, then all of these forcing terms vanish identically. And so physically what this corresponds to is just the entire water column advecting the Eddy field, like so. So there can be no transfer of energy to the vertical. If L1 is not equal to 0, then we can show that these coefficients achieve maximum values for values of L1 plus L2 equal to plus or minus a third. That should be actually plus or minus a third L2, which in any case says that the tide must vary on scales on the order of the Eddy field. Okay, that's assuming isotropy in the Eddy field. Okay, and the slow time dependence of these forcing terms up here can be solved for by going back to our Eddy and barotropic tide order epsilon equations and eliminating terms that will force or that satisfy the equations that satisfy the homogeneous equations. So when we do this, and a big thanks to this wonderful program called Mathematica, we end up with two coupled equations for the slow time evolution of the Eddy and tidal amplitudes, which roughly look like this. Generally speaking, it's not non-trivial to solve. One thing we can do is to write either u sub t squared as just a function of the Eddy amplitude, or u sub e squared as just a function of the tidal amplitude. And when we do that, we can end up with an equation where on the left we just have the time evolution of the Eddy amplitude, and on the right the time evolution of the tidal amplitude. Generally can't solve it. On the other hand, if you just assume that the Eddy amplitude, for example, is equal to 0, then you get inverse temporal behavior for the tidal amplitude. So what this says is that the product of these two will go as 1 over the time. you can do the same thing for u sub t. And if du sub t dt1 is equal to 0, then the eddy amplitude must decrease as 1 over the time. So I haven't solved the general slow time evolution, which is hopefully more interesting. And from our numerical simulations, actually, it seems that this case does not occur. At least we haven't seen it. We see a more interesting case where the amplitudes don't just decay with time. And so I'll just give you a summary of this weakly nonlinear analysis, and with applications to the ocean. For the deep ocean conditions, the barotropic tide scale, horizontal scale, is very large. And therefore, as I showed, even if resonance conditions are met, this interaction will be negligible. Now, in retrospect, maybe this was obvious, but we worked out the details and showed this. In coastal regions, on the other hand, where the tide can vary on much smaller scales, that is, on the scale of the eddies, this resonant interaction can be significant, but I seriously doubt that it is as important as the tide topography interactions. I showed that the tide and the teddy and the eddy fields may both act as catalysts, but in this case, then the forcing terms decay as 1 over t. And finally, this conclusion, which is, again, maybe not that surprising, but this mechanism is unlikely to be an effective generator of waves. And therefore, the Rogachev et al. Papers, their speculation, I think, is not correct. I'll just stop here.
Thank you very much. Time for
I'll
questions.
just put this up, and anybody who's interested can talk to you. Yes.
Yes.
The revolution equations, can you show them again, please?
The evolution equations?
For
Marie-Pascale.
UE and UT? Yeah.
Yeah.
So this is supposed to come from, because this is triad, right? So there is one triad which is, one component of the triad is like a forcing.
Right. So one component of the triad is the forcing, which gives rise to this u sub t.
Right. So you
Right.
have only two unknowns.
Yes.
And no, you don't know any other conservation law for this system?
Well, I mean, in that sense, it's not like a triad, because in a triad, the energy can just kind of go back and forth between the various components. In this case, the energy
is pumped into the system by forcing.
what?
The energy is pumped, is brought into the
Yeah.
system by forcing.
Right.
So
It's brought in.
So that
right.
could be a conservation law. That could give you a hint of conservation law that you can then try to check from this equation. If you have that conservation law, you can integrate the system. At least, or find some more structures. But I would, have you done numerical simulation of this system?
Yes.
And is it like a periodic, or I mean, does it have some
So-
quasi-periodic behavior, or just a decrease?
Well, it's periodic and it grows in time.
Ah,
Okay.
yeah, okay.
And
then
the A, B, C, D are just numerical values? Or
No, these are complicated expressions that depend on the scales of the eddy and of the tide. So,
But they don't depend on time.
Independent of time?
independent of time,
Okay.
yes.
Yes, Mike.
Can you give us just a hint of anything that's different about the numerical simulations than you get for the weekly nonlinear analysis?
Well, well, I haven't solved this full problem.
You just
Right.
did the thing you showed us at the beginning, did you? You ran what happened?
Right. Oh, what happened? Well, okay. Several things happened. First of all, there's always a certain level of imbalance. Okay, because no matter how careful I set up my field. So there's always a certain level of imbalance. Once those waves die away, then in a then the wave field can be set up if the resonant conditions are exactly
But
satisfied.
it's still weak.
But it's still weak.
That's the point,
Well-
it's still weak. It doesn't affect your final conclusion.
No.
That's all I wanted to know.
Other comments or questions?